Great, welcome everyone. We're so pleased to have you joining us for the final presentations of this year's University of Washington Data Science for Social Good program. My name is Sarah Stone, and I'm the Executive Director of the UW eScience Institute, which has hosted a DSSG program each summer since its inception in 2015. More broadly, the eScience Institute serves as a hub for data-intensive discovery on the UW campus, working with researchers from across all fields to use data science tools and techniques to advance their discovery process. During the past 5 years, we have truly seen a proliferation of data for good efforts, which are now pervasive in academia, industry, and the public sector. As data science as a field has matured, we have seen its enormous potential for societal impact. While at the same time, we are struck almost every day by examples of the unintentional and intentional hazards and inequities of using data in the social sphere. As a community and through this program, we are exploring and defining the space of using data responsibly, understanding the inherent importance of bringing a diverse community of practitioners to the table. Today, you will have the honor to hear from our student fellows dispersed across the country who have spent the last 10 weeks working entirely remotely with their project teams. Our 8 student fellows were selected from a pool of over 150 highly competitive candidates and represent diverse fields of study. Each fall, we have a broad call for proposals open to projects originating in academia, government, nonprofits, and industry. The project proposer commits to spending the equivalent of 2 days per week throughout the 10-week program, guiding their project team. Each team also includes eScience data scientists, the core of our institute, who provide technical leadership and support. These teams work very closely together throughout the summer, and as you will see, are able to do amazing things. This year, our program became entirely remote, which posed many new challenges and, I dare say, opportunities. Our program would not have been possible without the generous new support from a Micron Foundation Advancing Curiosity Award, which supported student stipends and remote work resources. We are also so grateful for the continuing support from the University of Washington for this program. Today, we are delighted to be joined by Nancy L. Alberton, the University of Washington Frank and Julie Jungers Dean of Engineering. In her capacity as Dean, she serves as the Chief Academic Officer of the College of Engineering and provides leadership to over 279 faculty and more than 8,000 students. Alberton is an international expert on multiplexed single-cell assays, microfabricated platforms for high-content cytometry combined with cell sorting, and microengineered stem cell-based systems for recapitulating human organ-level function. 4 companies have been formed based on her research discoveries. Alberton holds an appointment in the UW's Department of Bioengineering and is a fellow of the American Association for the Advancement of Science, the American Institute for Medical and Biological Engineering, and the National Academy of Inventors. We are pleased to have her join us today. Welcome, Dean Alberton.
Thank you, Sarah, for that fantastic introduction. And I'm really thrilled to have this opportunity to say a few words for this session on data science for social good, and really to celebrate the students and their amazing work. I'm absolutely thrilled to hear more about the students' work through their presentations today. And I think social impact work really resonates with the college. We really want to work with data science for social good and other avenues to really change the lives of people for the better. And this is a high priority of the College of Engineering. And again, I'm just really quite impressed by this year's topics on voting rights and disinformation in the time of COVID. It really is the right time for both of these initiatives. In particular, the college is really involved in stepping up to the plate to help with diagnostics and therapeutics, but also misinformation through our newly formed Center for the Informed Public. And again, I also just want to thank Micron, who has really done so much for the college and for UW for providing access and opportunities for our students to participate in data science for the social good. I think their Micron's support really exemplifies the impact that a strong alignment between two organizations around leading social challenges can really make a difference, both in the data science and the DEI space. And knowing this important role, I am just absolutely fantastically excited to be able to introduce Sanjay Mehrotra, the Chief Executive Officer of Micron, to share a few remarks about the students and community. But I want to say that I'm absolutely really amazed at Sanjay's career. He's been the Chief Scientific Officer, or Chief Executive Officer for Micron Technology since May 2017. And we all are using and have benefited for these projects, and they've made technologies, and they've made really huge impacts in our life. Prior to Micron, Sanjay co-founded SanDisk, who probably many of us know about also, and served as their CEO. Further, he holds 70 patents and has published numerous articles focused on non-volatile memory design and flash memory systems. So I just had a chance to talk with him, and I can say that he's really committed with working with the University of Washington, helping us build a strong talent pipeline into Micron, and is really committed to diversity and equity, which I think aligns with all of UW as well as my own. Sanjay, welcome to the forum.
Thank you, Dean Albritton. I just had a chance to talk to you right before this session here, and I'm hugely impressed with what's going on at University of Washington, and certainly University of Washington is very lucky to have recruited you as the Dean. I'm looking forward to the opportunities between your university and our company in terms of really driving research at the university, engaging a more diversified population of students, and of course, building a strong pipeline of talent, not only for Micron, but for America and for global good. You are seeing me wearing a mask here because I'm addressing you from my office. And as you can well understand, during COVID times, those of us that are in the office, of course, we have safety protocols of physical distancing and mask implemented. I just urge you all that please make sure when you are in public spaces or in your own office, please be wearing a mask at all times, and encourage your family members and your friends also to wear a mask. We all know what a difference it makes in terms of combating COVID, and we all have to do our part in flattening the curve. I'm really excited to be here today because I want to listen to the two presentations related to misinformation as well as with respect to vote dilution. These are, of course, extremely important topics, and these are topics that are related to data as well. For those of you who do not know Micron, let me just introduce Micron to you. Micron is a 41-year rich company, always pioneering data technology solutions. We are the only company in the US that develops and manufactures semiconductor memory and storage solutions. So some of you may know what DRAM means and what flash means. This is what Micron has led, and the company has more than 43,000 patents over its 41-year history. So just imagine, that means 1,000 patents a year. That means 3 patents a day. So while we are spending some time here, just imagine some of our innovators, some of our engineers are really creating patents as we speak. So this is the kind of company that Micron is. And of course, over this, by the way, I too have been in this industry for 40 years now. And I have to tell you that even though things appear as hard as they do today in the COVID times, from the point of view of semiconductors, from the point of view of memory and storage, this is the most exciting time to be in our industry. Of course, we have to work together, all of us, to get through this very difficult period of COVID. But I'm really talking about the exciting opportunities that are ahead of us That's what builds my enthusiasm. And what is that related to? It's all related to the fact that everything today is about data. It's all about data economy. Data lives in the products that Micron makes. DRAM and flash, this is where your data, the Zoom call that we are having, of course, information is going through the kind of products that Micron makes, facilitating the Zoom call today. When we think of cloud, cloud relies on more memory and more storage. Our smartphones, the pictures in the smartphones and all the wonderful apps that we run, memory and storage is at the heart of enabling those applications. Autonomous vehicles, automation, robotics, smart factories, smart cities, all of these rely on increasing amount of data. I'm excited for the long-term opportunities here because when you think of cloud to intelligent devices at the edge, it's a virtuous cycle. It's a virtuous cycle where more and more data is being created, more data is being processed, information and insights being drawn from that data to ultimately make intelligent decisions that impact our lives, that enrich our lives, as well as create new business models. And the opportunities being created through data are not only for the cool experiences that we may have through the smart gadgets in our hands, or not only through new business opportunities that get created. Data is really helping us solve some of the biggest unsolved problems of the world that have stumped humanity forever. For example, data is being used to now find cures for diseases that have been incurable so far. For example, we are at the heart of some of the institutes that are doing cancer research and finding cures for cancer, relying on tremendous amount of data to do that work. Of course, COVID, finding therapeutics and vaccine, data is at the heart of doing that research as well. So exciting opportunities for data, and the new trend that has evolved over the course of last few years in terms of being deployed across the globe, across the spectrum of industries, is AI. And AI, of course, the technology and the algorithms have existed for a long time, but today, the connectivity, the CPU capability, and data storage solutions all come together so that those software algorithms of AI can ultimately be deployed commercially to get the full value in all walks of our life. And so this is very exciting time. It has been said that AI is most exciting thing that has happened to this world since electricity. So just imagine the opportunities that lie ahead of us. We have barely seen the tip of the iceberg here. But when we talk about AI, it is about extracting intelligence from data. And that fits in really well with Micron's vision. Micron's vision is transforming how the world uses information to enrich life for all. And the for all piece is extremely important because when we talk about AI, when we talk about data-driven solutions, we want to make sure that no one is left untouched or unimpacted or not realizing the benefit of it. And that's why it's important that data solutions, the AI algorithms today, have ethics, have privacy, have integrity, and have security built into it. So this is extremely important. Those of you who were there in 90s when internet came around, of course, now we see that how some of the laws and regulations were not applied early enough to internet, and that led to some of the abuse of internet. It's important that when we look at AI, now is the time to understand how to tackle the difficult challenges of privacy, of security, and of ethics with AI so that data is used for good, not abused to create violations of ethics or violations of human rights or impacting some human lives. So this is why Micron, as part of its security grant, is really pleased to sponsor research across various universities, driving use of AI for the good of humanity. And today, hearing here some of the initiatives that you're looking at, these may be small steps in terms of ultimately understanding how AI really is used in ethical ways, but these are actually very, very important projects. These are the kind of things that academia, industries like Micron have to engage together to continue to drive this AI revolution that is ahead of us. We have barely begun. We have barely scratched the surface here. I think really exciting opportunities lie ahead. And I'm so inspired by the young minds and the really experienced faculty that is driving the collaboration together with the industry, with Micron, in terms of continuing to advance this agenda. So with that, I would pass it back to Sarah here so that we can get going with listening to our student presentations here. Thank you.
Thank you, Sanjay. I'd like to thank you very much for your dedication individually, and also the dedication of Micron to supporting our program and these broader initiatives in the same space. I'd now like to invite our first team to share their screen. And let me stop sharing so they can work to do that. The first team that you're going to hear from today is going to be talking about identifying coronavirus disinformation risk on news websites. I just want to remind everyone that there is a Q&A button that's usually located at the bottom of your screen, and you can type questions into the Q&A option at any time, and we'll field the Q&A questions at the end of each presentation. So we anticipate having about 5 minutes to share and to answer questions following the presentation. So without further ado, I'll turn it over to our first team here, and thank you all.
Thank you, Sarah, and thank you all for joining us today. We're excited to talk to you all about the research that we've been conducting over the past 10 weeks to develop an automated method to identify online disinformation related to coronavirus. And first we'll introduce ourselves, and then we'll go straight into our talk. So my name is Luetke. I'm a doctoral student in epidemiology at Indiana University.
My name is Kseniya Husak, and I'm a Policy and Information Studies Master's student at University of Michigan.
Hi everyone, my name is Richa Gupta, and I am a master's student at Columbia University.
Hello everyone, my name is Chidziwisano. I'm a PhD student in Information and Media at Michigan State University.
Additionally, we'd like to recognize the critical contributions from experts at our partner organization, the Global Disinformation Index, Maggie and Lucas, as well as the data scientists at the eScience Institute, Noah and Vaughn. As you all know, during the first half of 2020, coronavirus spread rapidly across the world, resulting in the current global pandemic. And as of today, COVID-19, the illness associated with the coronavirus, has caused more than 170,000 deaths and 5.5 million reported cases in the United States. However, what's not being reported in these estimates is the number of people who have died or spread the virus due to disinformation. And these false claims, such as the one that you see in the slide here, have led to people resisting wearing masks, as well as avoiding engaging in other crucial prevention measures. But most importantly, it's led to many preventable deaths. With the spread of the virus, there has been this corresponding proliferation of related health information online, with a great deal of this being false or misleading. And this glut of information, particularly disinformation, has made it really difficult for individuals to find the accurate health information they need in order to appropriately respond to the ongoing pandemic. It's also led to general confusion and distrust, making it more difficult for health authorities to disseminate the latest scientifically supported information about the virus. And lastly, it's led to numerous injuries and deaths from fake treatments and cures. For example, people have presented at hospitals having ingested bleach, hand sanitizers, and even fish tank cleaners, due to disinformation, and several of them have actually died. Disinformation exists for a couple of reasons, but one of the main ones is that it's profitable. This type of content is designed to generate a lot of traffic and clicks online, and that results in profits that mostly come in the form of ad revenue. This figure here shows that the major tech companies and the corresponding amounts that they will each pay out to disinformation sites in 2020. And overall, experts from the Global Disinformation Index, our partner organization, estimate that advertisers will provide approximately $25 million in ad revenue to coronavirus disinformation sites in 2020. So our project aims to address the social problem of disinformation online. However, it's a really complex issue for several reasons. First, as I mentioned in the previous slide, disinformation is designed to catch people's attention and generate lots of traffic. However, it's also designed to deceive. And one reason that it's so difficult for humans to differentiate disinformation from legitimate news is that the most convincing or persuasive disinformation content is that which catches on and spreads virally, reaching the greatest number of people. Second, disinformation domain experts know what to look for and therefore are able to distinguish disinformation from legitimate news much better than the average person. However, using domain experts and human moderators to do this is both time-consuming and expensive. And lastly, disinformation claims and narratives are constantly changing and adapting. Specifically, disinformation related to the coronavirus has exploited some of the initial and ongoing uncertainty about the virus, as the medical and scientific community has tried to play catch up and understand how to prevent and treat this new virus. For example, initially it was thought that the malaria drug hydroxychloroquine might improve outcomes for COVID-19 patients, but that has since been disproven by clinical trials.
Disinformation is harmful both online and offline. There are various factors that motivate people to spread disinformation online. As Maya mentioned, one of these factors is to gain incentives. The Global Disinformation Index focuses on disrupting, defunding, and downranking news websites that proliferate disinformation for financial gain. The GDI works collaboratively with ad exchange companies and other platforms to rate the risk of disinformation on news websites. Our project is supported by the GDI's resources to train a machine to identify coronavirus disinformation risks in news articles. This contributes to the GDI's initiatives by extending disinformation identification from domain level to article level on websites. In addition to giving this domain level overall score, our project will provide an algorithm to classify articles on news websites. The data for our project was provided by the GDI. Our data was scrapped from news websites across the internet. These articles were written between May and June 2020. The data specifically contained over 28,000 articles about coronavirus. A GDI expert with high credibility had labeled these articles as legitimate or having disinformation. Our data is imbalanced towards legitimate articles than disinformation articles. We conducted pre-processing to remove noise from our data. As earlier specified, our data was scrapped from news website, so it had some noise in them, for example, embedded links. We removed these embedded links, duplicates, and words that carry less meaning, such as they, at, and this.
Once we have the clean data, it is then ready for the next step, which is the classification algorithm. In our project, we are using a neural network as our classification algorithm. The word neural is connected to the word neurons in our brains, and very similar to how our brain learns information, a neural network, when it sees inputs, it tries to draw patterns, it remembers those patterns, And when it sees an unseen input, it tries to draw inferences from those patterns to classify the unseen input. A very common example of this is the spam email filters. A spam email filter is trained by multiple spam emails and non-spam emails. And the filter learns to identify patterns that are present in spam emails, so that when it comes across a new email, it looks for those patterns and is thereby able to identify whether this new email is spam or not. Similar to that, our neural network will be able to classify when it comes across a news article, whether that article is disinformation or legitimate. As you can see in this image, the neural network has 4 layers. In each of these layers, the black dots are the neurons. These neurons are connected to the neurons that come before it and that come after it. If the neural network is passed a disinformation article, a few of these neurons get activated. They transform that input and pass that transformed input to the activated neurons in the next layer, and so on. Eventually, the model is able to identify the input that was given to it as disinformation. And the same process will happen for the legitimate text articles as well. This activation and transformation process is the pattern that the neural network will then remember for the next, for the new articles. Now the question arrives, how are we going to feed a text article into the neural network? And the answer is, in our project, we converted the text into a list of numbers. Very similar to how we understand text, if we come across 2 sentences, cat sitting there and dog resting here, despite the fact that these are 2 different sentences, we will be able to identify that cat and dog are somewhat connected because they share some similar features. For example, they're both animals, they both look cute, and our brain will be able to put cat and dog in similar buckets, despite the fact that these are 2 separate sentences. In a similar way, our neural network will be able to draw some commonalities between the words that are presented to it. And with those features, it will give a similar list of numbers to words that have common features and a dissimilar list of numbers to words that do not share much in common. And to train this list of numbers, we used articles that were outside of our corpus, outside of our training data set. And we did this so that we can make our list of numbers more generalizable, so that we are not too domain specific, so that we are able to generalize trends across time as well. And the next step that we performed in order to improve the performance of our model was that we not only looked at what words appear in the text, but also how they appear. We also paid special focus on the context in which the word is appearing. For example, the sentence, "The pandemic has been tough on our people. While there have been some signs of recovery, coronavirus has put us in a challenging position." The algorithm will be able to see that the word pandemic and tough appears together in a sentence. Similarly, the word coronavirus and challenging is appearing together they are appearing in the same context. And the algorithm will be able to give similar list of numbers to these words: pandemic, tough, coronavirus, challenging. And in short, what we try to do is we try to judge a word by the company that it keeps. Not only that, we also trained our model across various sets of parameters so that we could optimize its output.
Choosing the right metrics for model evaluation is as equally important as choosing right model and features to feed into it. So when building the classifier, our 2 main goals were: 1, maximize detection of disinformation, and minimize misclassification of legitimate news. The first one is kind of a no-brainer. That's the goal of our project. The second one is worth explaining a bit more. Here's where it's useful to step back and think about the context in which we are trying to accomplish our task. Access to accurate information is absolutely essential for people to navigate through the health crisis we're all living through. So it's important to have legitimate news out there and to have a model that will not disincentivize it by blocking it from revenue it needs to be out there. So in terms of how our model performed, of the 2,420 disinformation articles in our test data set, our model correctly classified 2,268 of them. That's a 93% correct prediction rate. And it's a pretty impressive result that made us really happy. What about the other metric? Of the 4,685 legitimate articles, our model incorrectly classified 131 of them as disinformation, which is about 3%. That's still a really good metric. But still, when we saw these results, we asked ourselves, what could be happening here? Neural networks are extremely sophisticated, and we were kind of expecting a little bit more. And we thought that perhaps by understanding why legitimate news are being classified as disinformation, we could gain insight into how to tweak our model. So we went back to look for an explanation. Here's an example of a legitimate article that was labeled as disinformation. The title says, 5G conspiracy theories are vicious. We must battle the virus of falsehood. It's actually an article that talks about dangers of disinformation in the times of COVID. It is likely that our classifier picked up on this article because it actually contains disinformation, but in a completely different way and context. It does not propound it, but rather talks about it. And this made us realize that any machine learning model can probably make this mistake. Based on text alone, an article that talks about disinformation is very challenging to automatically classify and is likely to confound any model. But the purpose of this tool is not to be perfect. Rather, it is to greatly reduce the workload on people who are trying to combat disinformation. According to a 2006 paper by Vaughn and Apollo, humans are, on average, slightly better than chance at being able to identify disinformation. In fact, GDI spend a lot of time hand labeling their data. It's very unlikely that we can actually automate away disinformation. Human intervention is central to the success of our classifier and any classifier. But we hope that when deployed in conjunction with human review, we can minimize disincentive of legitimate articles that talk about disinformation narratives while trying to catch as much disinformation as possible. So where do we go from here? Is our work done? Well, we have a couple of recommendations. One, neural networks are often criticized for the black box problem. The question of neural network interpretability is under much discussion and scrutiny at the moment, and it's actually an extremely rich area of research that we just did not have time to go into given the timeline of this project. But it is something to be taken into account of and explored in the future. Features. We focused on using article text, and we stripped out all of the URLs. But could embedded URLs add precision to our model? Could analyzing a network of URLs that are embedded in the text help us reduce false positives, that is, help us reduce incorrect prediction and make the classifier even more reliable? Again, something to be explored. And then there's the algorithmic decisions. There are so many different network architectures and hyperparameters. We tested 72 permutations of them, but there are a million different combinations to try out, and this is just a prototype. We were limited by time, and we think we produced a pretty good model, but sky's the limit, so a lot more work can be done there. In terms of how this work can be used, well, when we created this model, our intent was for it to be useful to GDI as well as other researchers. One thing to keep in mind, our model was trained on data scraped, March through June, but we think that you actually need to retrain the data. So when the GDI decides to play around with it, retraining it is going to be extremely important because disinformation narratives are changing super rapidly and you want your model to stay current. It is also a very powerful tool, and like all things algorithm and classification, it's got ethical considerations behind it. So we are really confident in handing this off to GDI because we know they will put in place the precautions and procedures so that the model is not misused on the internet. And lastly, we think that GDI will find this model useful to be used perhaps in other topic areas outside of COVID-19. We're also hoping that by putting this code out there, making it open source, we're going to contribute to a huge effort that is being led by many research teams out there, and it can be actually useful to other teams that are working on the same problem. And with that, we'd like to conclude the talk point of our presentation and open up the floor for questions. Thank you so much.
Fantastic presentation. Hopefully you all are joining me in doing, I'm just going to go ahead and clap and you guys can hear my claps and know that those claps are resounding throughout this virtual room. Wonderful job. So why don't you continue to share your screen in case there's questions where you want to flip through the deck. We do have some questions coming in. And so I'll go ahead and share the first one here. So this is from Ali Ajmiri. He asks, are those companies intentionally procuring and distributing disinformation, or is it a lack of due diligence on their part to filter disinformation?
I can go ahead and take this one. So the answer is no, that they're not, these ad tech companies are not intentionally funding disinformation sites through ad revenue. The thing is that as we emphasize, it's really difficult to identify disinformation, and the ad tech companies are not able to identify disinformation websites in this really quick process of buying advertising space, which happens kind of in the seconds before a website loads. And the partner organization that we worked with, Global Disinformation Index, is doing great work here where they are working with ad tech and advertisers in order to provide that information about disinformation risk of websites. And then the advertisers and ad tech can make decisions to not give ad revenue to those sites.
Great, thank you. The next question is, what's the topology of the network? Is it feed forward or RNN?
I can take this. So it's a recursive neural network, and I wouldn't like to go into too much technicalities, but it's a bidirectional network which is able to learn the context of the words from words that have come before it and after it as well.
Okay, thank you. So when you are looking for patterns in text that are characteristic of disinformation for an established corpus, such as hydroxychloroquine, there are lots of materials to learn from. When a new topic like oleander emerges, there is no corresponding corpus to compare it with. How does your neural network deal with emerging misinformation topics compared to more established ones? This is, I think, something you started to touch on at the end of your talk. Yeah.
I can take that one. Yeah, so it's only going to be as good as the data we feed into it. So which is why it's important to retrain your classifier with newest data as much as possible. That would be the solution. So if a new narrative about oleander emerges, then you would want to retrain it, and then that's how you deal with it.
Great, thank you. Let's see, we have a couple kind of related questions here. Where's the link for the code and the model, and will the data be open source as well?
I can take this one. So we are still finalizing our website, and once we have finalized it, we'll have like a link on the main DSSG website where you can go to our website, and the code will also be available on GitHub. And but the data is private; it's for GDI, so it will not be public.
Great, thank you. And I'll just note too that we'll be following up with pointers to the full websites that these teams are building out, where you can dive into this information much more deeply as well. So take a look for that coming up. Let's see, next question is, got some great, you're really driving a lot of questions here, you guys. Let's see, are there other pre-processing steps that could be performed to improve the model?
I can take that one. Well, kind of piggybacking off of what we said, we actually extracted a bunch of linguistic features, whether it is part of speech features or a number of embedded URLs, the types of embedded URLs. article headlines. So we did not include that in this model version, but we think that you could absolutely add more features, more of those features, right? It's not just about the semantics behind the words, but it's also how it's written and you know, other stylistic choices that people make when they write disinformation. So absolutely, there could be more. We've already processed it, but we didn't include those features in here.
Great, thank you. All right, what is the reason you chose neural networks in the first place? Can you describe that decision process?
I can take a stab at it. So it was a very contentional point, because we had a lot of discussion about what type of model do we want to use. And I think eventually we decided to use neural networks for the performance that they produce. And yeah. Essentially, it was a great learning opportunity for us also to identify what are the state-of-the-art models that are being used for natural language data, and neural networks came out as a winner.
Thank you. Let's see, we'll take a couple more questions here. Let's see, could you go back to the correct prediction rate you showed and clarify if that's accuracy or precision?
So that's actually taken directly from a confusion matrix. That's how many articles were predicted correctly, knowing that they were labeled as disinformation. That's the rate. So I hope that's a satisfactory answer.
Okay, great. What's your view? So we'll wrap this up with a last question here. And those of you who've also asked questions in thread here, please know we just had a lot to go through, and it's wonderful that this presentation has generated so much discussion. And please feel free, and we'll make that available, to reach out to these teams following the presentations for further clarification. So let's see, what is your view on the feasibility of using unsupervised learning in the future to avoid the overhead of training labeling processes?
I can take this one. So it would be feasible, like to use unsupervised learning to train a model for disinformation, but this is a very sensitive area. So still, maybe there would be some. A model might not be 100%. So there would be a need still, like for humans, like to still like cross-check those false positives, for example, and see, maybe just verify them to see whether they are really like false positives or not. So still, even like if we still have unsupervised learning, human intervention would still be needed.
Great, thank you. Actually, there's one more question here, I think, that would be a nice wrap-up kind of question. And kind of, anyway, just want to get to this last one, which is, were there any interesting features, patterns that the model found to be indicative of disinformation? I know this was something you didn't have quite time to fit in your talk, so I thought you might appreciate the opportunity to speak to it a bit.
Yeah, I think, okay, I can take it. So I think, honestly, I think one of the major things that the model is able to catch on are a few words that occur more frequently in association with the word coronavirus. And that would be one of the biggest predictors. However, just like highlighting the black box nature of the neural networks, it's not like 100% transparent to identify what those features would be. But I think one of the things that we want to do is go back to see the output that the models have produced and try to interpret more of the outcomes. And I'm sure we would be able to understand it much better then.
Thank you, Richa. Okay, well, let's give a final round of applause to our team, and thank you very much, student fellows, for a wonderful presentation, and very slickly done, considering that you're all distributed across the country and have been this whole time. So we'll move on, if you want to stop sharing your screen, and we'll move on to our next project team. Our next team is going to be presenting on detection of vote dilution, new tools and methods for protecting voting rights. And go ahead and take it away, you guys.
All right, thanks, Sarah. Thanks to everyone again for joining us today. I will start off our presentation that I'm super excited to give you guys today. We worked this summer to make sure every vote counts by improving an R package to detect vote dilution. So we, the fellows, will be speaking today. It'll be myself, my name's Hikari, along with Ari, Juandalyn, and Pratik. So we'll go ahead and get started. So to start off, I know I can't see you, but this is just a little exercise to get your mind starting to kind of warm up to this idea of vote dilution. I want you to raise your hand if you vote. I actually can't vote, I'm not a citizen. And if you think that voting is important to democracy, so raise your hand again. I guess we have the raise your hand feature. So I guess everyone really does think that to have a working society with a democratic nature to it, voting is a key component to making sure that our society works. So even though we all think this is important, under the hood, we don't necessarily know what happens to our vote once it goes into the system. All right, so do you know if voting inequality still exists in your system? So this could be happening at the local level or the national level, depending if you're voting for a school board official or if you're voting for our president. Or do you know if your vote is actually being diluted, or do you even know what that means? So let's break it down from there. So voting systems can actually dilute minority voting power. So I want to make this really clear to you all what that actually means. So in our example here, we have a population that's blue and yellow. It's 60% blue and 40% yellow. And as an entire group, they are looking to elect 5 individuals for 5 seats. So in this non-diluted case that I'm showing here, we have 5 seats that we are voting for. In our case, in this one, we have wards that are horizontal rectangles, and this ensures that we have 2 yellow wards that could elect 2 yellow preferred candidates elected. But now let me show you 2 ways that voting dilution can actually occur. So in the left example, we have an example where we have cracking. So this is where the yellow population is spread out among all 5 wards, and they are unable to elect any seats that their demographic prefers. So we have 5 blue seats. And then we have at-large voting, and this is where the entire population votes for every seat. And in this case, all seats could be candidates preferred by the blue population because they are the majority. So this is actually prohibited by the Voting Rights Act, but it happens more often than you think.
An example of a case where voting dilution has occurred is in the case of the East Ramapo School District elections. The makeup of the East Ramapo School Board is a result of an at-large voting system, where every registered voter in the district can vote for each candidate running for a seat on the board. The current board consists of majority members that racially identify as white and religiously identifies as Hasidic Jews. And this has been the demographic of the board for over a decade. This board has acted to increase funding to the religious and private schools that their children attend, where 98% of the students racially identify as white, and have acted against the interests of public school students of the minority population, which consists of Black, Latino, and Asian students. And within the public school system, only 2% of those students are white. So not having equal representation on the school board for over the past decade in this case has led to adverse outcomes for minority students, such as low teacher funding or staffing, large class sizes, and ultimately low graduation rates. So in the case of East Ramapo and other cases like it, how do we ensure equal representation? How do we make sure that your vote counts as much as your neighbors? Through using the Jingles test. This test came out of the 1986 Thornburg versus Jingles case, and is how we prove that voting dilution exists. There are 3 criteria to be met in order to prove voter dilution. The first being that the minority group is large and geographically compact, in order to establish themselves as a majority in a single member district. The second being that the majority voters are politically cohesive or voting for the same preferred candidate. And third, that the majority population votes with the goal of defeating the minority group's candidate. So if we can't prove that there is a minority group that is both large and compact for criteria 1, it will be much harder to assess points 2 and 3.
So one of the reasons why points 2 and 3 of the Jingles test are hard to prove is that US elections are confidential, like many around the world. As such, we can never really know who voted for which candidate. Take a look at this table. It tabulates all the votes cast in a particular election in the election precinct in East Ramapo. At this precinct, just under 10,000 votes were cast in a recent election. We know from looking at election results that just over 7,000 of those votes went to candidate A, and around 2,500 went to candidate B. We also know that 8,400 of the voters were white and the rest were minorities. But we don't immediately know how to fill in what goes inside this table. For example, did almost all white voters vote for candidate A, or were they split between the two? And with minority voters, it's even harder to tell what's going on. It's possible that all 1,300 of them voted for candidate A, or that all 1,300 of them voted for candidate B. Requirements 2 and 3 of the Jingles test require the minority voters vote cohesively in favor of one candidate, while the majority cohesively votes in favor of the winning candidate. To see if this is happening, we're going to need to fill in this table. Luckily, the field of political science provides us with a tool we can use to get at the preferences of different groups of voters, and this is called ecological inference, or EI for short. Ecological inference is a Bayesian statistical technique that takes advantage of the fact that elections take place across multiple precincts. Think about elections you participate in. Maybe at your voting precinct, most people are of one race, but at a different precinct somewhere else in the city, the racial makeup is different. EI looks across all precincts in an election for patterns and uses these patterns to estimate the numbers that go into the table. As a simple example, in non-statistical terms, if it appears consistently that precincts with more white voters also tend to yield more votes for a certain candidate, we can use ecological inference to conclude that white voters might generally prefer that candidate. So in cases like East Ramapo, we want to run ecological inference. But first, we have to do some work. We need to gather election results and figure out the race of people who showed up to vote. It's easy enough to get election data. To find out who voted, we can go to voter files. So these are data sets maintained by states and counties that contain lists of every voter who has voted in elections in that region. These typically include voters' names and addresses. Most of the time, voter files don't have information about voters' race, which we need to conduct ecological inference, so we have to estimate their race first. We can use BISG to estimate the race of voters. BISG is a well-established tool from the fields of biostatistics and political science for estimating the race of individuals on the basis of their surnames and where they live. But we can't run BISG directly on the voter file, and this is because BISG requires entering voters' locations as latitude-longitude coordinates, like on a map. So to get these coordinates from voters' addresses, we need to do what's called geocoding the addresses. Now we see the full pipeline of what it takes to conduct ecological inference. First, we geocode the voter file, then we run BISG to estimate the race of voters, and only then can we run ecological inference. And as any data scientist will know, the pipeline is actually even more complicated than this. In between each of these technical steps, there are a multitude of little steps, including data cleaning, merging, aggregating, researching the best tools, quality control, and so on. EI Compare is a software package written in the R programming language that provides functionality for end-to-end ecological inference in the context of elections. EI Compare was initially developed prior to this summer by our project leads, Dr. Matt Barreto and Loren Collingwood. And this summer, we worked to expand its functionality, add additional statistical robustness, and make it more accessible. Now let's see it in action.
Using the pipeline of the EI Compare package, we will assess what happened in the East Ramapo School District election. After receiving the voter file, the first step is to ensure that the voter addresses are geocoded. By geocode, we mean find out where voters live using points on a map. Geocoding is a brand new part of the package that didn't exist before. In the past, users would have had to do this step on their own and validate that the geocoded addresses were indeed true. Remember, one of the first criteria of the Jingles test is to prove that the minority group is large and geographically compact. This is typically done by demographers who figure out how the minority groups are clustered. We geocode or convert addresses to latitude and longitude points that we can put on a map of our geographic area of interest. However, in our quest to know if East Ramapo has areas within it that contain minority populations that are geographically large and compact, we now need to know the race or ethnicity of each voter. So let's take this voter with the surname Jackson living on Leaf Lane, for instance. How will we find out the race or ethnicity of this voter?
So our end goal is to get the racial composition of precincts. And to do so, as Juandalyn said, we're going to obtain probabilistic estimates of each voter's race using a method called Bayesian improved surname geocoding, developed by Elliott et al. In 2009. Now, eICompare relies on another package to actually perform the BISG called WRU. This was developed by Imai and Kana in 2016. But we've developed helpful utility files to successfully run this package in our pipeline. Now, let's take that voter that Juandalyn showed before, the voter with surname Jackson. This surname can be mapped onto a census database of surnames. According to this database, 39% of people last name Jackson are white, while 53% are Black. Let's focus on these two racial groups for now only, just for convenience. We can think of this as a prior knowledge of the probability that this person is white or Black. However, we also know the address, which we've geocoded, and we can map that geocode onto a geographic unit called a census block. Now, the census also provides demographic information about each of the blocks. And in this case, the census block is 80% Black. So this increases the probability that this voter is Black. Now, using Bayes' theorem, we can update the prior knowledge provided by the surnames with the additional knowledge provided by the location to come up with the final probabilistic estimate of race, as shown on the right. Importantly, what we're going to do is we're going to aggregate these probabilistic estimates across voters in a precinct to come up with a final racial composition per precinct. That's going to serve as the input to the ecological inference.
So now with all of that work done, we can actually run our ecological inference. So as Ari mentioned before, we have this table that we don't know quite what the values are, where the question marks are. So we can actually fill these in now to figure out the proportions for a racial group voting for a certain candidate. So once we run EI, we can see that the majority of our white demographic prefer candidate A, around 7,000, and the majority of our minority constituents prefer candidate B. So now that we have all this information, how can we make this more convincing and show not tell? So eICompare has capabilities to create visuals for us so that we can prove our case to the court. So this is an example of one of those visuals. So this is a density plot. On the x-axis, we have percentage of white voters who voted for a certain candidate. On the y-axis, we have the probability, or where the peaks are show the most likely value for the percentage of voters that come out of EI. So this graph is for white voters. We can see that candidate A is preferred at around 80% of white voters voted for candidate A. And for candidate B, it's around 19%. Okay, so now that we have this, let's compare it to the density plot of our minority voters. So we can see that the blue and yellow peaks are switched. The yellow is for candidate B, so the minority voters prefer candidate B. So this is the end product of eICompare and is one tool that we can use in litigation and create these visuals quickly and easily. So we've proven that each demographic seems to have a strong polar preference for one candidate over the other. And with that, we can cross off the second point for the Gingles test. We can even run eICompare for multiple years to assess whether the minority group is cohesive throughout those years. And now by proving that across history, we have the basis to start proving point 3, where the majority votes in a block to defeat the minority-supported candidate. So let's take a look. So we can look at the school board election results throughout the years from 2015 and onwards. So let's take a look. So we have 3 blue seats for 2015. So the majority preferred candidate won all 3 seats in 2015. And we can look at 2016, 2017, 2018, you get the point. So minority voters consistently voted for the losing candidate, while the majority voters consistently voted for the winning candidate, and the minority candidate never won. So this means we can cross off 0.3 for the Gingell's test. And now we've proven that minority vote dilution existed in these school board elections.
This evidence for vote dilution produced by eICompare was presented earlier in May to a judge in a voting rights case, presented by plaintiffs, the NAACP, and NICLU, which is the New York division of the ACLU. Our project leads were actually expert witnesses in this case. The judge sided with the plaintiffs and found that the voting system, which is an at-large voting system in East Ramapo, diluted the minority vote and was unlawful, and struck it down. So now what? At-large voting is struck down in East Ramapo. The judge ordered that the system be switched to a ward system containing 9 wards, each of which corresponds to 1 seat on the school board. Both the plaintiff, NICLU, and the defendant, the school district, had to propose new voting maps for the district. Now, East Ramapo here is shown in the middle in red, and we're given 2 maps for it. The NICLU map, the plaintiffs, is shown on the left, and the defendant map for the school district is shown on the right. Each of these 2 maps look similar, but they have differences in their divisions. Now, Hikari discussed earlier that even a ward system can result in vote dilution if the lines are drawn in the right way. So how do we look at these 2 maps and tell which, if either, provide adequate representation to minority voters in the school district? Our approach is going to be to simulate past elections using these maps. In other words, we'll assess their performance by running them in past elections. We know who voted from the voter file, and we know where they are because we already geocoded them. So we can actually run the election and examine where the minority voters turn out to vote in which wards, and then determine how many seats they would have won if these maps had been in place at that time. And these are the results of our analysis. Now we're showing the same maps as before, with each ward color-coded by the minority turnout. Now we've outlined the wards in which the minority turnout was sufficient to win a seat on the board. And the NICLU map on the left, there are 3 wards in which the minority voters earned enough vote to win a seat on the school board, 1, 2, and 3. These are outlined in white. On the other hand, the defendant map has only 2 seats in which the minority voters would have won seats on the school board. Now, wards 3 and 4 in this map have some elevated turnout, but it's much, much less than the other 2. And if we look at Ward 3 on the left in the NICLU map, we can see that this ward, which is high density minority population and turnout, was cracked into 3 different districts, 2, 3, and 4. And that explains why there's 1 less seat on the school board for the defendant map. That even though we have a ward system, the vote is still diluted through cracking. This evidence was presented to the judge in the ongoing court case, and she responded favorably to the NICLU map. We hope to hear good news in her decision soon.
So this summer, we worked to improve eICompare. We added many new features to help users move cleanly throughout the process of conducting ecological inference. And this includes the addition of geocoding functions where previous users had to figure this out all by themselves. We also improved the core BISG and ecological inference functions. We sped them up, we added new visualizations, we improved their handling of uncertainty, and much more. This is a long list of all the improvements we made to the package and all the ways we applied the package to conduct research throughout the summer. If you would like to learn more about voting rights litigation, or would like to see tutorials on how to use the package, check out our website linked here. Or if you're ready to dive into the code, check out the GitHub repository from which you can download eICompare and get right started using it.
We don't want to stop with East Ramapo. The census is happening right now, for which the results will inform the drawing of new district lines at all levels of government in 2021. We anticipate that eICompare will be heavily used in a multitude of impending voting rights cases, as these new districting lines are tested for vote dilution. In an effort to support this, we spent a lot of time this summer meeting with a variety of stakeholders, including NICLU, the New York division of the ACLU, who was involved in this East Ramapo case we talked about, the National ACLU, the National Democratic Redistricting Committee, the UCLA Voting Rights Project, and the California Citizens Redistricting Committee. All of these stakeholders have a vested interest in supporting equitable districting. We hope to carry forward these relationships as the fight for voting rights continues. I want to thank our project leads, Dr. Matt Barreto at UCLA and Dr. Loren Collingwood at Riverside, now at New Mexico, for leading us throughout this entire project. It was a wonderful experience. And thank our data scientists, Spencer Wood and Scott Henderson, who provided us countless feedback and technical expertise throughout the entire summer. And also thank our sponsors, and want to thank you all for listening.
Wonderful. Thanks, you guys. And let's do a round of applause as much as we can in the virtual space. I clap loudly for you. Thank you. So please drop your questions in the Q&A box, and go ahead and I think this team is going to field their own questions if you guys want to go ahead and select which questions you'd like to answer.
Right, so I see one question about, is the software package open sourced? And if so, how can people contribute? So this is an excellent question. As we mentioned earlier, the package is available on GitHub currently. And we plan on releasing it on CRAN, which is ours open source publishing service, by the end of the week. We also hope that people will contribute to this package moving forward. It's available on GitHub, and people can make their own pull requests there and try to add new functions and post issues as well. Yeah, so definitely encourage people to contribute to the package, as well as it's accessible to anyone to use.
There's another question about how to get data so you can test out some of the work that we've done this summer with EI Compare. And actually, you can visit your state website for voter registration and actually download the voter file. They're all publicly accessible, but some do ask for fees. So you would have to make sure you have the means to do that. But we can also send you a link to an example of voter data within the EI Compare GitHub page, which we also have tutorials or vignettes that you can walk through using some voter information there.
I'll start off answering another question, and I think the rest of the team can chime in if they would like to. So the question is, how do assumptions of ecological inference hold in political reality? And do you have any data to validate these assumptions? So we've used EI Compare for East Ramapo, obviously, as we walk through the example with you all today. We've also used it for data in Georgia and other cases that Matt and Loren, as well as our other stakeholders, have been a part of. And some of the ways we've kind of tried to see how this actually works alongside, the election results you might see on the news, like related to Georgia. We've ran it through, we've used, Georgia actually reports race for their voter files, so we can use that as a basis to assess if that really works for seeing if the election results match up with the results from EI Compare. And we're planning to kind of work with that a little bit more and then see how we can do actual error propagation through our other analyses, which I think other people can speak to.
And to add on to that, the situation in the US is often pretty suitable for, unfortunately pretty suitable for the assumptions made by these EI techniques, where it's often very segregated and there exists racially polarized voting. The ecological inference problem is actually more general than just in the voting realm. It comes from ecology, and it can be used in a variety of other fields. And so some recent work trying to reframe this problem as a machine learning problem have looked at these EI techniques and assess how they performed in a variety of contexts. And it turns out that these techniques that we're using, these Bayesian models, actually still perform exceedingly well when you have exit poll data to validate the results, even if there are newer techniques to evaluate them. So it's the conditions in the political realm that are suitable for EI.
And so there's a question here. Someone asked about our analyses in Georgia, and if there's any results we can share from there, looking at the disputed governor's election. So we did do some preliminary analyses there, and they seem to suggest, perhaps unsurprisingly to those familiar with the election, that there was a lot of racially polarized voting going on there. So white voters tended to prefer Brian Kemp, and minority voters tended to prefer Stacey Abrams in that election. Of course, those results remain preliminary. We plan on conducting a more thorough analysis and possibly turning that into an academic publication. And the great thing about Georgia is that in Georgia, voters actually report their race on the voter file. So we're able to compare the BISG estimates to actual self-reported race. And then we can compare our EI results to exit poll results that are available for that election. So that Georgia example gives us an opportunity to kind of validate or test the entire pipeline.
You guys have time for probably about one more question.
Okay, there's a couple of questions here about like the accuracy of BISG, which has been touched upon. So we can go ahead and answer those. So like in particular, like was there any way to perform error propagation on the race determination analysis, which is related to the accuracy of BISG? So this is ongoing work right now, and we hope to complete it even as the summer ends. Succinctly, what we're doing is we are modeling the census, and the census information provides the racial demographic information that goes into BISG. So we are modeling that as a sampling process with a probability distribution, and we'll use that to propagate errors for the BISG calculation. And that'll better inform the output of BISG. And then, as Ari mentioned, we'll compare that to cases where we have race on the voter file to assess the conditions in which BISG performs well or doesn't perform well. There's been some past research on this. And then hopefully improve on BISG using other types of information. So one thing we're looking at is using first names to better inform the calculations of BISG in terms of the posterior estimate of race.
Okay, you can go ahead and take one last question.
Juandalyn, you want to answer the question about geocoding at the end because you worked so hard on it?
Yeah, so I just seeded the question, I think, in the answer column of the chat, but we actually went through a process of figuring out and comparing geocoders with a set of data to figure out which ones accurately gave us close latitude and longitude points to where we think these voters exist, so within that region of East Ramapo school districts, for example. And we ended up using the US Census Geocoder API, which gave us pretty accurate points and was able to locate most of the addresses that we needed to move on to use BISG.
So I wanted to note that you know, this program is probably, as you can tell, normally done in person. And so when the pandemic hit, we thought deeply about whether to attempt to transform what we all thought of as sort of an inherently in-person experience into the remote sphere. And we arrived at the consensus of the importance of offering this type of hands-on training experience to students, especially as we saw some of these opportunities disappearing or certainly decreasing. And hopefully when you look at this, this photo, you'll laugh along with me. But you know, we were worried about how teams would gel and work productively together. But as you can see, our project teams, through the work that you've just seen, their remarkable work over the course of the summer, and hopefully these pictures also display as well that they were able to overcome these challenges, and we were all able to become colleagues and friends over the past 10 weeks. So I'd like to just give another round of applause and appreciation to our students who, you know, took part in this sort of great adventure and yeah, I guess, yes, not knowing sort of where any of us were going at the time. So we're very much looking forward to a time when we can all get together in person, and we've even talked about what that might look like. I also want to note that running a program like this is complex, and especially rapidly transitioning to a new medium was truly a team effort. Over 70 people participated in and supported this program in all kinds of ways, from joining us on career panels to teaching tutorials or being available on Slack language helplines. Within eScience, we are truly lucky to have such a dedicated and talented group of individuals who constitute the core of this program. In particular, I would like to call out DSSG Program Chair Anissa Tanweer, who you can see in the middle here, Anissa Mountain Goat. I'd like to call her out for her leadership, guidance, and insight, which have really been invaluable to the development and maturation of the UW Data Science for Social Good program. And you'll see some of the other folks who were very deeply involved in the program this year, and a very much extended thank you to all of those I couldn't fit on a single screen. And lastly, I want to thank all of you for joining us today. As I mentioned previously, you can expect to receive a follow-up email from us with a link to these presentations, as well as to the project websites that the students are wrapping up this week. And you'll be able to learn a lot more and hopefully answer some of those unanswered questions we didn't get to today. So thank you all for joining us. Cheers and goodbye for now.